So today we're going to be talking about ideal gases. Um, Essentially, we're talking about gases that are in the perfect kind of conditions. Um, Gases are one of the more interesting topics for these states of matter. Essentially, we're going to talk about, when we talk about gases, we talk about three kind of characteristics that a molecule has, that if they have them, we can say that they are gases. So gases must be able to do these three things. First thing, they're easy to compress. So by easy to compress, what I mean is that if we have like some kind of container, and I have like a bunch of gas in there, I should be able to add some kind of pressure and make it so that all those gases are kind of being pushed down on top of each other, so they can be pushed together. That doesn't really work with solids or liquids. They kind of just stay in their general area. A second big property that they need to be able to do is they have to expand to fill their container. So again, if I have like that container and I have like the gas molecules inside, if I were to make a bigger container, then those four gas molecules should spread out to fill up that volume. So that's going to be your second property. Third property that must be present in order for you to consider something a gas is it needs to occupy or fill more volume than a solid or liquid. Because at the end of the day, we're just comparing like solid, liquid, gas and seeing which takes up more volume. So in regular chemistry, we kind of talked about how solids, they're all going to be kind of packed close together. Liquids are going to be a little bit more spread out, but usually kind of clumped in like the bottom of whatever container you're looking at. And then gas is going to be like all spread out. So these are the three properties that must be present in order for you to consider a molecule a gas. So when we talk about ideal gases, there's this idea called the kinetic molecular theory. Of gases. Essentially what this means is there are kind of 5 conditions that help us explain how gases behave. So 5 behaviors of ideal gases. 5 behaviors are 5 kind of, I guess the better word for this, instead of behaviors, better word would probably be like assumptions. These are 5 things that we expect an ideal gas to do. So the first one, I will give you kind of like the actual, they're kind of called postulates. I'll give you the actual postulates and then we'll kind of simplify them. So the first postulate states that gases consist of these small, tiny particles. These tiny particles could be either atoms or molecules. But these particles are going to be so small when you compare like the distance between them that the volume of the individual particles can be just assumed to be 0. So we can kind of simplify that to just say, first postulate, gases are so small compared to the volume that we assume the gas molecule has no volume. So that's basically what that first postulate says. We're going to simplify that to just say gases are very small, or gas molecules are very small. Should probably specify that. So gas molecules are so small they take up no space. So we just kind of assume that the molecules are there, but they're not taking up any of the space of the container they're actually in. The second postulate is essentially just saying that particles are in constant random motion. They're going to collide with the walls of the container, and that these collisions of the walls cause pressure to be exerted by the gas. Particles have random motion and will collide with container and then those collisions cause a pressure, well, a force, referred to as pressure. So that's that second postulate. We are going to simplify that, and we're just going to call the second postulate random motion causes pressure. Our third postulate is that molecular collisions, so like when the molecules kind of hit each other or hit the container, these collisions are going to be perfectly elastic. All that means is that when the gas molecules collide, we don't lose any energy. They don't slow down, they stay at that same speed, they have the same amount of kinetic energy before and after the collision. So essentially, molecular collisions are perfectly elastic. And then we're just going to simplify that idea that no energy / speed lost as molecules move in their container. Our fourth postulate is going to be that the average kinetic energy of the gas particles is going to be proportional to Kelvin temperature of the gases. So it essentially means that the higher the temperature of the gas, higher energy of the gas. KE just stands for kinetic energy. If I put the line above it, it just means average kinetic energy of gas particles is going to be directly proportional to temperature in Kelvin, degrees Kelvin. Just simplifying that idea just means at higher temperature, we get faster speed and faster speed means more energy. Because kinetic energy, just a little aside, is 1/2 your mass times your velocity squared. Well, speed is just going to be your velocity part. Okay, and then the fifth and final ideal gas property. There we go. Is that gas particles are not going to attract or repel from each other. There's just basically no interaction. Gas particles will not interact. And when we talk about interact, they do collide, but we're talking about like forces. So to simplify that, fifth postulate, we're just saying that there are no attractive or repulsive force between gases. So essentially, these are our 5 kind of assumptions that gases will follow as they're interacting. Gases are going to be really small compared to their container. Gases will have random motion, and in that random motion, it's going to create pressure when it hits the container. Your gas molecules are going to have no energy or speed loss. So whatever energy or speed they start with, they will end with. We're also assuming that at high temperatures, your gas is going to move faster, meaning your gas has more energy. And then finally, that there are no attractive or repulsive forces between your gases. These are going to be kind of like the 5 assumptions that we make. So based on these assumptions, there are kind of 5 different measurements that we can take. Or we'll stick with 4 for now. So 4 measurements when we talk about gases that follow this or these 5 assumptions. So the first measurement we can take is pressure. Basically asking, when those gas molecules collide with the container, how much force is exerted. So pressure, we'll usually use the variable P. And again, essentially what we're asking is, pressure is the force on container by gas inside. Now, the real definition of pressure is like something like a force that's exerted by a thing per unit area on another thing. But since we're talking about gases, our definition for pressure is going to focus on gases. It's going to be the force of a container, a force on a container by a gas inside. So essentially, we're just talking about when those gas molecules hit the sides of the container, how much force is exerted on it. Usually the units of measurement we use for pressure is going to be Pascal, which is PA. Essentially, Pascal is just how much pressure is exerted. 1 Newton of force of pressure over like a meter squared, something like that. Just know that you could see Pascal. You could also see kilopascal. It's going to be kPa. Kilopascal is usually a little bit more common. But these are the two kind of units that we use most often. There are some other units you'll see sometimes. Sometimes you'll see ATM. This just stands for like atmospheres of pressure. That's like another common one. Some that are a little bit less common are going to be like millimeters of mercury. That's pretty old. We normally don't see that one as much. You might also see torr, or you could see bar. They're not as common. The most common one is going to be Pascal or kilopascal. ATM also comes up fairly often. And then millimeters of mercury, torr, or bar, those are like the least common ones you'll see. So those are all like the metric measurements. Being in the US, sometimes we do use imperial units. You're not going to see it on the AP test, but you should just know that the imperial units are going to be PSI. So that's like what you fill your car tires with. You'll also see inches of mercury. So those are going to be like your standard international. But we're going to focus on the Pascal, kilopascal, and the ATM. You might see some of the other metric units, but for the most part, those are going to be the two that you see. So next, we can talk about, we'll do volume next. So volume, kind of the same process. We'll use that first letter as our units. So for volumes, we'll call it V. So volume is going to be how much you can fit in like a three-dimensional space. But for us, we're going to say the amount of space a gas takes up. So essentially gases fill up their entire container. So essentially what we're asking is, how big is the container? Most commonly, the units you're going to see for volume are going to be liters. So liters, we'll use that letter L. You'll also see milliliters. Should be an I. So ml, those are probably going to be like the two most common you'll see. You might also see a little bit less common, going to be meters. Or cubic meters. Cubic meter is going to be m cubed. It kind of just depends on the type of question you're given. Normally, you'll see liters and milliliters on the AP test. I have seen meters and cubic meters also used. Meters, cubic meters, it's more commonly used for like rooms and stuff. So those will be like more like practical, real life examples. Liters, milliliters is usually used more in a lab setting. But given that our lab is going to be all about gases, we're going to be using liters and milliliters. Next quantity we can talk about for gases is like the amount of gas. So to talk about this, we're going to bring back that idea of the mole. So we're going to use the letter N for that. So again, the idea of a mole is it's kind of like a dozen for atoms. So if I have so if I have something like a dozen donuts, there's 12 dozen in a donut. When it talk about atoms, for 1 mole of atoms, I have 6.02 times 10 to the 23 atoms in there. Quick rundown for the mole. Essentially, this problem is when we're doing research and we're doing labs and stuff, it's really hard, near impossible, to get a single atom because there's a ton of atoms. So instead, we just get kind of like a standard measurement. The mole is going to be based on the molecular or atomic mass of atoms. So essentially, if you get 1 mole of an atom, that's going to correspond to its atomic mass on the periodic table. So what they did a long time ago, they got a certain amount of carbon, they measured how much that carbon weighed, and they said, okay, for 12 grams of carbon, it's going to equal 1 mole. And they just compared everything else to that carbon, and that's where we got this standard idea of a mole. It's just based on the atomic mass of carbon. So when we talk about amount of gas, the moles, we're just talking about how many units of gas you have. So we'll say how many units / bunches of gas atoms. You should just know that 1 mole is equal to 6.02 times 10 to the 23 atoms. It's going to be a little conversion factor, and we might use that a little bit later. So the thing about moles is it doesn't matter what the mass is. All atoms are going to take up the same amount of space. So if I have like 1 mole of helium and 1 mole of, we'll say, like argon gas, so both of these are gases, they're going to take up the same amount of room. So molar mass of helium is going to be about 4 grams per mole. The molar mass of argon is going to be about 40 grams per mole. So I just got those numbers based on the periodic table. If I were to fill up a container with 1 mole of each gas, they're going to take up the same amount of space. So all of those particles will take up the exact same amount of space. Okay, so the last thing we need to talk about is temperature. For that, we'll use the letter T. Temperature is different from heat. Temperature essentially is going to be kind of like a measure of how much energy is in the system. So last year we talked about how Q equals M times C times delta T. So we talked about how Q was energy, and change in temperature, well, that's your temperature. So this is like heat energy, or like kinetic energy. So we said these two things are different. temperature is related to energy, but they are not the same thing. So when we talk about temperature, although those two things are similar, temperature is going to be a measure of like the internal energy of a system, while heat is more of a measure of like how much energy is moved from one thing to another thing. Essentially what we're talking about is temperature is going to be like how fast the molecules are moving. That's like an easy way we can think about it. Now again, not 100% true, but it's a simplification to help us kind of understand what temperature is doing. And then this kinetic molecular theory kind of explains this idea that the greater the amount of heat energy that a gas absorbs, the more rapidly those gas molecules are going to be moving, and we can measure how that movement increases by the temperature increasing. In reverse, if atoms start to slow down their movement, it means energy is going out of the system, things are getting colder. So essentially, these are going to be the kind of foundation for the gas unit. So, quick summary. In order for a molecule to be considered a gas, 3 things have to be true about that molecule. First, it has to be easily compressed. Second, it has to be able to expand to completely fill the container it's in. And then third, it has to fill up more volume than the solid or liquid variations for that molecule. If all those things are true for a molecule, we consider it to be a gas. Now, when we try to describe the behavior of a gas, we're kind of assuming 5 things for that gas. If all 5 of those things are true, we would say we have an ideal gas. First thing that needs to be true is that the gas molecules need to be so small that they take up relatively no space. Second thing is that your gas molecules are going to have completely random motion. Third thing is going to be that when those gas molecules are hitting each other or bouncing off the container, that no energy is lost, meaning those molecules are not going to slow down. Fourth thing that needs to be true is that at higher temperatures, your gases are going to move faster, so they have more energy. And then the fifth thing that needs to be true is that those gas molecules are going to have no attractive or repulsive forces between each other. If all 5 of those things are true, then we can look at these 4 things for a gas. We can look at the pressure of the gas, we can look at the volume of the gas,